Hello, everyone. Thank you very much for having me, and thank you very much for coming to this presentation. It's the first talk after lunch. I'm not sure if this is good or bad, but at least I hope you're still hungry for some additional knowledge on quantum computing. Let's start with a quick question. So, who attended the previous talk by my colleague Branislav and Professor Bushak? Okay, that's great, because now you know much more about the physics of a quantum computer than I do, to be honest. And on top, you learned a lot of about the basics of quantum computing, so I can mostly skip that, right? So there were already a couple of questions what this thing is above there, and this is how actual quantum computers look like, at least those made by IBM, right? So this is an actual quantum computer, or at least a model of it, and quantum computers these days look like this, right? So the technical details and the physics, I'm sure, can be explained by Professor Bushak and Branislav much better than I could do, so I will skip this here. But I first want to tell you what we are actually talking about. So in the previous talks, we were concerned about the physics and quantum mechanics of such computers. What we will do here in this talk, and it's the first time I use chalk in, I don't know, more than 20 years probably, is I'm talking about a black box that we call quantum computer, and we do not care about what's going inside of this quantum computer, right? So the physics and the experts are sitting over there, please ask them. What we are discussing here in this call is basically what is going in this quantum computer, what is going out of this quantum computer, and what are the characteristics of this quantum computer and the transformation of input to output, right? So that's what we're basically going to discuss in this talk. And let me first begin with a quick introduction who I are and who we are. So who am I? Basically, I'm a computer scientist loving to look into complicated topics like quantum computing, and doing this now for a couple of years. We at Accenture look into quantum computing now for more than 7 years, something like that, 7 to 8 years. And since then, we basically evolved to one of the leading quantum computing delivery companies and have about 100 resources globally contributing to our quantum computing practice. We do a lot of research, so we have many patents in the area of quantum computing and much more. We are partnering with many of the industry leading companies, and of course we are offering a lot of projects and project support to our customers in the area of quantum computing. So if you are interested in Accenture Quantum and some demos that we have online, please visit that link. There you can find a lot of details. Now, the question when we talk about quantum computing is always, why shall we look into quantum computing? And this is one of the typical definitions that you can find, right? So quantum computing has the potential to solve intractable challenges in this decade. Disruptions are expected across all industries. So let's be honest, this is basically consultant lingo and terminology, and no one really means what that or really knows what that actually means, right? So what does intractable mean? What does challenges mean? And what are disruptions in this case, right? And to motivate that a little bit, let's have a look at this, right? So if we think about subatomic particles and their energetic evolution, a classical computer would take easily multiple millions of years to calculate just for a few particles the next time steps, if you like, right? But the point is that this is something we would call intractable. So if you're really interested how subatomic particles evolve over time, you cannot simply wait hundreds of thousands or even millions of years, because you actually need to do your drug discovery or something in the area of chemistry now, right? And the point here is that nature, for some reason, please talk to the physicists, they know that much better, do that more or less flawlessly all the time for the entire universe. And now the more or less obvious question is, can we exploit that? And in the previous talk, we already heard that Feynman is one of the most famous physicists who sparked that discussion. I, as a computer scientist, always need to add that there was a computer scientist 2 years earlier than Feynman who raised that topic, but typically it's attributed to Feynman, right? And this question can be answered, and obviously the question is yes, because if we cannot exploit it, I wouldn't have a talk today, right? So the benefits of having quantum computers and quantum algorithms, as we'll see, is that at least we hope that we can use less resources for solving computational problems. And now, obviously, the next question is, what does less resources mean from a quantum computing perspective? And here are some examples, right? So time, memory, storage, energy, and messages. But the most important resource we're typically talking about is time, right? So that is the most precious resource that we have. Storage and memory is comparatively cheap. Messages somehow count in distributed communication and algorithms, but typically we're talking about time in this context, right? So there's a rich literature on all of these other resources as well. But in this talk and in most other talks about quantum computing, we're focusing on time, right? So in the future, energy might also become pretty important. As we will see later on, we can save hopefully a lot of absolute wall clock time when we try to solve complicated problems. And then, of course, we use and consume much less energy. And yeah, the next question is, what is a computational problem? This question was raised approximately 100 years ago, and there's a lot of theoretical frameworks floating around. So maybe you know the lambda calculus, and they tried back then to formalize exactly what a computational problem is. But this is beyond this talk, so we just go with that simple informal definition. So a computational problem is any problem that a mathematician can solve with pen and paper, or at least try to solve, right? But these are some nitty-gritty details we do not need to discuss here. So this is the informal definition we go with here in this talk. But to make it a little bit more practical, here is an example. And many of you probably have heard about the traveling salesman problem, which is, the statement is pretty simple, the task. So there are a couple of cities, so these nodes there. And we start at the green node, and now we find a round tour, visiting all of these cities, so all of these white nodes, and then finally arriving again at the green node. And now the question is, how can we do that? How can we find an optimal solution for that? And I know this looks pretty trivial, and for such small instances, you can do that by just eyeballing at it, right? But if you do that for more cities, let's say 100 cities, and a lot of connections, so roads basically between these cities, this becomes intractable. So if you use a naive algorithm for solving such a TSP for 100 cities, you can easily wait for multiple thousands, if not millions of years before you get an absolute optimal solution for that, right? So the question here is, can quantum computing help? And to answer that question, we need to go back one step. Why does it take so long to solve such a problem? And the answer is that there are some proofs, as long as p does not equal np, that you need at least an exponential number of steps here. And since pandemic situation, we know how worse exponential growth can become. So this grows pretty fast, and it takes a lot of time to solve such instances. Now, we answered the question if we can exploit that. The question is, how can we exploit it? And what you can see here on the left side is basically the physical part. So what you've seen in the previous talk. So superposition, entanglement, tunneling effect, and some more quantum mechanical effects that are important here. On the right side, you see something that is related to the actual computing, right? So maybe you know the classical gates for classical computing, and, or, and so on and so on. Similar gates, but much more complicated, also exist for quantum computing, and out of these gates, you can build circuits, and as explained in the previous talk, at the end, you can do some measurement to get information out of such a circuit. And how or where do we apply such circuits? Well, basically the basic entity of data, in this case, are not bits, as explained in the previous talk, but qubits, right? So you have there the possibility not just to represent zeros and ones, but a linear combination, so a superposition of these two values of 0 and 1, and basically you have then just a mixture of these two states. And as Professor Buschek explained in the previous talk, at the North Pole, typically we have the 0, and at the South Pole we have the 1, and every other point on the sphere's surface could be another linear combination, so a superposition of these two basis states. And with that knowledge, physicists build quantum computers. So these quantum computers, as we will see later on, run quantum algorithms. And the important fact here to state is that a quantum computer per se is not faster than a classical computer. And that is not the point about doing quantum computation. It's not about executing a single step. So for example, a quantum computing gate faster than a classical gate. It's more about saving steps, and that is what the quantum algorithms do. So quantum algorithms exploit these quantum mechanical phenomena like superposition and entanglement and so on, and come to optimal solutions, or at least they converge faster than any classical solutions, at least for a couple of problems. And to be a little bit more precise, what this actually means, we need to dig a little bit deeper. So the question is, what can quantum computers actually do? So the first statement here is that quantum computers solve at least the same problems as classical computers. So that basically means that quantum computers are an extension of classical computers. But this is somehow trivial, right? The more interesting question is, can quantum computers solve anything more than classical computers? And the answer is, unfortunately, not, right? So there is not a single problem in the world that a quantum computer can solve that a classical computer can't solve. You might ask why, and the reason is pretty simple. About 110 years ago, there was a lot of discussion exactly about this problem, if there could be a more futuristic computers like quantum computers, and whether they can solve additional problems or not. And as we have defined computational problems as these problems that can be solved by pen and paper, it has been basically shown that a classical computer can already solve all possible problems. Hence, there couldn't be any single problem that could not be solved by a classical computer, and hence there couldn't be any additional problem that might be solved by a quantum computer. So where's the difference if the set of problems are equivalent? And that is the right side here. The first difference is that for an exact optimization, so for example, for the case of the traveling salesman problem where we want to know the perfect solution, quantum computers can solve them at least polynomial faster, and we'll see an example of that later on. And for some kind of problems, we can even solve them exponentially faster, right? And if we're not that much interested in a perfect solution, we're talking about heuristical algorithms or learning algorithms like quantum neural networks, for example, which we'll see later, right? And here the idea is that for optimization, we have a rich literature and a lot of results. And in the past 20 to 30 years, there was a lot of success in finding such algorithms. And there are indeed some algorithms. We've heard, for example, about the Shor algorithm already, which basically cracks RSA by being able to factorize very large numbers. That these algorithms are pretty successful. For the second part, so heuristics and learning, the literature in the theory is not yet that clear. This is basically ongoing research, I mean, for optimization as well, but compared to heuristics and learning and heuristics is bleeding edge, right? I mean, basically the scientific society community is talking about this, basically since the approximately 10, 15 years, I would say, at least the majority of these researchers, right? So to sum up, what a quantum computer can do is that we could save steps and require less steps to find an optimal solution, or for heuristics and learning algorithms, we converge faster because as we will later see, we can exploit that we have a high-dimensional vector space that could be used to actually find solutions, for example, in a neural network. And the second point is that quantum computers do run algorithms, not applications. And from the previous talk, there were a couple of questions. Maybe you can answer them already by your own, right? So the first question, or one of these questions was, can a quantum computer run Windows? So any answers after seeing that? Any guess? Obviously not, because Windows is a quite complicated application written in C, I guess, or C++, whatever. And this, of course, will not run as it is on a quantum computer. Can you somehow turn it into a quantum program? So absolutely theoretically, yes, because we have seen a quantum computer can do the same as a classical computer, but you will never do that, right? At least definitely not in the next decades to come. So quantum computers are basically used as an accelerator for algorithms. The second question, or interesting question, was, can we simulate a quantum computer? So who thinks that classical computers can simulate quantum computers? And who not? The others? So it's a difficult question, but indeed, I mean, it's again point number 2 and point number 2. Point number 1 and point number 2. Since the set of problems that could be solved on a classical computer and on a quantum computer, yes, indeed, you can simulate a quantum computer on a classical computer. And you can do that every time, right? And on the last slide, I'll give you some pointers to some documentation and some quantum computing frameworks. And you can run a quantum simulator on your laptop this afternoon, if you like, right? So no problem. And this is pretty easy to do. Documentation is pretty good. Also, you can start working with a quantum simulation this afternoon, if you like, right? So we now understood at least roughly what a quantum computer can actually do. The question is now, where are they really, really good? And this is just an overview. We cannot go into all the details, but the idea here is that there are certain classes of problems where classical computers are pretty good. And this class of problems is called P for struggling with a classical technique, right? So, this class up here, P, stands for polynomial time. That means we can efficiently solve that on a classical computer, but that's not too important. More interesting here is that we see this left, let's call it an egg, right? So NP and the other egg BQP. And the reasoning and the notion about this is that in the orange egg are those kind of problems that could be efficiently solved by a quantum computer. And on the left side, so in the blue one, we see those kind of classes and problems where we at least know that a classical computer can't solve them efficiently. And by efficiently, we mean in polynomial time. That means more or less that you can run it even for large instances in a relatively short amount of time. And the really interesting part is now that overlapping part here, right? So we see that there are a couple of problems which are very difficult and hard to compute on a classical computer, but you can solve them in polynomial time on a quantum computer using the appropriate quantum algorithms. And one of these examples we have already learned about in the last talk, that was the Shor algorithm. So the Shor algorithm does not belong to this class up there, NP-complete, because we know about this class, which is a subset of NP, that there is no way to get an exponential speed up for these kind of problems, even on a quantum computer. Right? So we know, and that is basically here the semi-sweet spot, how I called it, we can get a polynomial, basically a quadratical speed up for these problems, but not an exponential speed up, what we basically want to get. And for this overlapping part, for example, Shor, so the problem of factorizing very large numbers, there we can get an exponential number, an exponential speed up. That does not mean that we can get an exponential speed up for all of these problems on the left side, which are not NP complete, but at least theoretically it's possible. And for a couple of problems, we already know quite some good algorithms. And just to give you an idea how this actually look like, right? So if we get a quadratic speed up, that would mean that a number of steps that might be 2 to the power of 100. So for example, if you have roughly 100 cities in the traveling salesman problem, you can bring that down to 2 to the power of 50. And the left one, the red one, right, that is intractable. If you apply the naive algorithm, you would wait more or less forever, so simply intractable. But it can bring it down to 2 to the power of 50, which is at least somehow solvable by applying the largest supercomputers that are available, right? So what we do is that we bring down complicated problems to solvable problems, which we can solve in, well, it also takes quite some time, right? But especially if you do not have access to large supercomputers, but at least it's nothing that we would call absolutely intractable, right? But it's even more complicated. So what about TSP now, just as an example? So we know that we could quadratically speed up the problem of solving this maze, basically, of the traveling salesman. But does that mean that we are now faster than every classical algorithm? Unfortunately not. It turns out that there is a faster classical algorithm even beating this quadratical speed up. So theoretically, in this case, a quantum algorithm, at least the Grover algorithm, would not help us. But a couple of years ago, another quantum algorithm has been discovered, and this in turn is now faster than the fastest known classical algorithm. So in this particular case, for the TSP problem, we know that we can solve that problem faster on a quantum computer, than on any classical computer. And the real thing that we actually want to get and where we want to benefit from is this sweet spot, right? So where we basically can get an exponential speed up so that we can solve even large instances. So for example, think about sorting or searching or, I don't know, calculating the shortest path, right? So this is particularly fast on a classical computer. And the idea of quantum computers is now to make other problems which are classically much harder also solvable in such a relative short amount of time. So the takeaway message here is that optimization, and that is the backbone of many machine learning algorithms, can drastically benefit from quantum computing. We can draw a similar diagram also for heuristics and learning algorithms. However, that is much more complicated, but we will see there's also some hope for that kind of algorithms. So what we've learned so far. So we understood that quantum computing is basically the combination of quantum computers and quantum algorithms. So the question is, where are we exactly now, right? So the largest quantum computer that is currently publicly available is one of these IBM machines, and they have 127 qubits, which doesn't sound a lot, and unfortunately that is right? So if you say that a qubit basically corresponds to a bit in classical computing, you know that a computer with 127 bits, you cannot do a lot, right? Of course, you can do some tiny problems and experiment with quantum computers, but to actually use quantum computers to solve large instances of some problems, we need much more. But the good thing here is that all of the vendors of quantum computing hardware try to stick to an exponential growth of these qubits. So by the end of the decade, that's one of the common expectations, is that we'll have quantum computers which can really tackle larger problems that we could do on classical computers. Well, and yeah, we also heard about quantum algorithms. A lot of potential, but at the same time, they're pretty tricky to understand and to program, right? And then, if we know that quantum computers are not that mature yet, and we know that quantum algorithms are not that easy to use, it's really interesting that we at least once per week see something like that, right? So some companies are claiming that they basically achieved quantum advantage for an arbitrary real-world use case. Is that really the case? The point is that typically these companies do a couple of, let's say, things and tweakings that they can release such a press release, right? So what they first do, they, in many cases at least, they do not compare the empirical quantum advantage, right? So quantum advantage means that we are better than every known algorithm, and quantum supremacy means that we are better than all classical algorithms. So typically we want to stick to the advantage thing, because supremacy, theoretically, you need first to prove that NP versus, so P is not equal to NP. But the point here is that quantum algorithms, so the green part here is just one step in the execution of an entire quantum processing pipeline, if you want to call that, right? So you have preparations on a classical side, you also have post-processing, and you have a quantum state preparation. And that, for some algorithms, require also an exponential number of steps, or at least a quadratic number of steps. And we've heard that that typically is the benefit that we can get out of quantum algorithms. But if you need to invest such time for state preparation, the result could be that empirically, for your entire chain, you cannot achieve any quantum advantage, right? And plus, on top, you have the problem that, as I explained, the quantum computers are immature in that sense that the size, for example, measured in qubits or some other metrics, are not yet good enough for really large real-world instances, right? So that is the current situation. But still, and this is important to iterate and to emphasize, is that when we are talking about quantum machine learning, and here we'll see an overview of the most common algorithms in that area, there are algorithms which are not only practically, but especially theoretically faster, even including the entire empirical data processing chain, right? And in this overview, I'm just showing you a couple of examples from optimization, because I said optimization, and you probably know that, is the backbone of many machine learning algorithms. So there we see, for example, quantum annealing. We've heard about that already. And there is no proven speed up for quantum annealing, to be pretty clear here. But where we know that it is faster is everything that is based on so-called amplitude amplification. And the most well-known algorithm based on that is Grover. So where we can get the quadratic speed up for any NP complete or any NP problem even. And some special cases, for example, TSP. So the fastest algorithm known these days for TSP is a quantum algorithm. And then we see clustering, regression, classification, and sampling. And there are a couple of algorithms where we have proof. So, for example, support vector machines on a quantum computer theoretically is even exponentially faster because of the underlying HHL algorithm, which we'll not discuss here, but it's basically about linear equation systems, right? But as I said, in total, it's much more complicated. If you want to look into the details of that, I recommend Scott Aronson. He's a pretty famous complexity theorist. One of his most famous paper on such topics, what the opportunities but also challenges of quantum computers are, is named Read the Fine Print. So there you can find all of the details, right? On the right side, you can find a quick overview where we are right now. So the green box down there, where we have a classical algorithm and classical data, is what we're doing now, right? And the more important, interesting parts, basically, I want to say, is the right column. So where we have quantum algorithms and, for example, quantum data. And there it has been shown just, I would say, 3 or 4 months ago, in June, I guess, that there is indeed a quadratic speed up. But quantum data means that we're talking about more or less a physical experiment where you get, for example, out of quantum sensors already entangled and superposed data, right? This is not what we typically call machine learning. When, for example, yesterday there was a session on fraud detection, right? So that is classical data. You have data in a CSV format or whatever, right? So where you have name and street and all of that, right? So this is not quantum data, but classical data. And there it has been shown that at least for some stilted and artificial problems, there is definitely at least a quadratic and sometimes even an exponential speed up. But it's still to be shown that we can also do that for large instances and for real world use cases. So in the interest of time, let's quickly touch upon this. This is, I would call it a sanity check or a reality check of the most common optimization algorithms. So quantum annealing. So I've said there is no actual proof that quantum annealing is really faster. However, there is the potential because quantum annealing is exploiting the quantum tunneling effect, and that mathematically speaking means that you could basically jump through local minima in an optimization function, right? And there's a lot of research going on in that area. Again, the problem that most of these publications have in this area is that they are not comparing the right things. So if you have a mathematical background, you might know what a optimization problem is in a rigorous way. So in this case, you typically use a quadratic, unconstrained binary optimization problem, so only binary variables and no constraints. And if you use a classical solver, Gurobi, Cplex, whatever, or any other kind of solving techniques for these kind of optimization problems, you know that these solvers are drastically relying on constraints that are available, because then you basically shrink the entire search space. And what these publications typically do, they optimize a QUBO on a quantum annealer and use the same QUBO on a classical solver. And then they claim, hey, look, my quantum annealer is much better than my classical solver. I have achieved quantum advantage. But this is not the right way how to compare it. The right way to do it is to use the SOTA approach, so state-of-the-art approach. And that would mean that you use the original problem formulation with constraints, and that typically, or at least in all cases I've ever seen, and in all the scientific publications, they come to the same result, that right now, with the quantum annealers available right now, the original solvers are still faster, right? Matter of fact. It could be that if these quantum annealers get bigger and bigger and the formulations get bigger and bigger because of the quantum tunneling effect, that there might be some results where we can actually see some breakthroughs, right? Then on the right side, we see meta-heuristics. We'll see that later on a little bit in detail. These kind of algorithms try not to find an optimal solution, but at least to approximate, so not an optimal solution, but to find and approximate a good solution, right? And there's a lot of potentials, but also for these algorithms, there is no confirmed case, if you want, where you have an advantage. But this is definitely something where a lot of things will happen in the near future, right? And then Grover, we talked about that. Yes, there is some proof that is pretty clear. Once the quantum hardware matures in a way that we have enough qubits, we can definitely run large instances on that and then gain this quadratic speed up from that algorithm. And of course, we have these specialized algorithms. So for example, TSP. So we know that there is no, at least right now, no known algorithm on the classical side that could solve a TSP instance faster than those quantum computing algorithms, right? And that's basically that in the box down there. Now let's come to the more quantum machine learning part. And here you see a framework, a learner framework. And if you've ever done some kind of machine learning on a classical computer, you will recognize that, right? So we have the input on the left side, and in the learner, we have a function approximator. So for example, as we will see in neural network, then you have a cost function, and at the end you have an optimizer, and then you start your iteration and your computation and learning once more, right? And for the function approximator, as I said, so typically these days use a classical neural network, but you can do the same on a quantum computer. So they can also build a quantum neural network, but the predominant way how to do it is, today at least, is the hybrid thing, right? So you have classical neural network layers interweaved with a couple of quantum neural network layers. And for the optimizer, typically these days you can use a classical solver. So maybe you know the gradient descent algorithm, for example. That's the grandfather basically of many optimization algorithms being used in such learner frameworks. But of course, theoretically, in future, you can also use quantum algorithms, and we have seen that these can bring a lot of value to the table, and maybe we can speed up learning and heuristics and so on in the future by using quantum algorithms here. So in total, on the left side, we've seen that this is the standard approach these days. Then we have the chance by using quantum layers to potentially get better approximations, and on the right side, hopefully if you can use quantum optimizers in such a framework later on, we also might benefit from that, right? So now let's have a closer look at a quantum neural network, and this is the same structure as on the previous slide, right? So we start with the input on the left side, then we do this embedding and state preparation for a quantum computer. Then you have this quantum circuit, so the capitalized U. That's basically the quantum circuit that we have here. And at the end, in the previous talk that was already explained, we need to measure, and then we get some distributions, right? So we're not talking about a deterministic output, but about some distributions over the output of the qubits, basically in very simple terms. And then you have the loss function and optimizer, and then you change your parameters and start your learning iteration again. So typically in classical terms, you call it an iteration, epoch, whatever, right? A lot of terms about that. So the general opportunity that we have here by leveraging or by exploiting these kind of neural networks is that we need to use much lesser data samples to train your network, and then to basically save a lot of time during the training of these neural networks, right? There are, of course, a lot of challenges. We'll not discuss here all of them, but the point is that the interesting part is that classical machine learning was very successful in the past years, and we know that it's difficult to beat them. But the interesting point is that quantum neural networks could, theoretically, there's a lot of ongoing research right now about that, excel exactly in those cases where classical neural networks, cannot excel, right? So there might be problems which are difficult to learn on a classical computer where quantum neural networks could actually excel and bring value to the table. Here we see even another iteration or another level of detail, basically. So on the left side, you know that, right? So we want to tell dogs and cats apart. So we have the classical input here, and then we need to, and that is the state preparation and embedding. On the previous slide, we somehow need to turn that into quantum data. We've heard about qubits and how this representation worked with complex numbers and so on and so on. Then we superimpose them. And what we basically, and this is the idea, we then have a vector space, and you can see these vectors here in a very high dimensional space. And what we then basically do is we just rotate them, right? And by rotating them in these layers of rotation gates, which have parameters like rotation angles, you can basically try to optimize the measurements that you'll finally get, at least the distributions, right? And in the interest of time, we need to speed up a little bit. But the idea here is that we go from dimension n to dimension 2 to the power of n. And if you ever heard about support vector machines or kernel computations and mathematics, you know that this might be beneficial for a lot of classification problems. And on a classical computer, you need to do that explicitly, basically, right? So going from n to 2 to the power of m dimensions, here you get this more or less naturally. And then you can do these operations parallel on all these superimposed and entangled qubits. The idea here is, and that is basically this picture down here. So you basically want to classify red and blue points in a two-dimensional plane. You can't do that, But if you turn that into a 3-dimensional vector space, in this particular case, it's like that all the red points are at the bottom and the blue points at the top. And then you can put there an n-1 dimensional hyperplane, so just a standard 2-dimensional plane in this 3D case to tell apart red and blue nodes in this particular case here, right? So the question is obviously where and in which cases can we benefit from that? There are some papers on that, but to be very honest, I will not show you some details here about, I don't know, we save 10% of parameters here and there. This is still ongoing research, right? So if you're interested in that, we can talk about that. But basically the idea is that there's a lot of potential for saving the number of data samples, and then you have the opportunity basically to converge much, much faster during your learning process. So just to give you an overview where these techniques are being used. So here's one of our use cases we submitted to the BMW and AWS Quantum Computing Challenge last year, which we won back then. So there the task is to find an optimal positioning of sensors, as you basically want to cover as much of the vicinity of the vehicle as possible. So you need to position sensors like cameras or radar sensors and so on, right? So there we use the quantum reinforcement learning approach, but also some quantum optimization algorithms. And in this part down here, some other colleagues of us are doing drug discovery by basically finding out how this ligands and protein interaction actually works and what the best solution is here. And the idea is, and that is really important, if you can speed up such drug discovery processes, in the end you can save a lot of time in, let's call it modern drug discovery, which is basically computer simulation, right? And there it's important to know such details. On the right side, just for the financial services industry, you see a couple of companies already investing in quantum computers because they expect a lot of disruption from that area, right? And as you can see, for example, Goldman Sachs and JP Morgan Chase, they're investing heavily in this technology already. Then let me come to my summary and then obviously to the questions. So for real-world opportunities, we have the chance to get a significant speed up for optimization and potentially even better machine learning approaches and converges. Later on, as I said, a lot of research is going on in that area. And then, we also need to discuss the limitations and challenges. The point here is that quantum computers run algorithms, not programs. We have discussed that already. The hardware definitely needs to mature. So there are a lot of forecasts on that. And as I said, the roadmap, for example, for IBM is exponential. So next year we'll have 250 qubits approximately, and then 500,000 and so on and so on. The point is that an advantage in terms of an actual real world use case, that is something that has yet to be shown in the future, but I'm pretty sure this will happen in the next years, probably in 5 to 10 years approximately. So you might then still ask, why shall you care about quantum computing if there is no real world use case yet? Well, the point is, you need, or at least your company and many companies, as you've seen on the previous slide, want to prepare for that disruption that is coming ahead, right? Then upskilling takes a lot of time. And of course, shaping the technology via consortia, for example, is also a very important topic. Thank you very much.
Thank you very much. This was Sebastian Senge. I don't think anybody could talk about quantum for less than 40 minutes. It's probably impossible. Maybe in 2 generations we can achieve that. But you missed your time for the questions already. So
we have 5 minutes left.
No, we don't. We're starting in 6 minutes with another presentation. Need to get coffee. But you answered mostly everything, and maybe the next guy from the bank we can ask him this.
Sure.
So next is Tomáš Horníček from VUB Banka. Thank you. This was Sebastian Senge. Thank you very much.